Okay, actually, now we have to ask the question: what is your n square? N square can be written as sum over n is equal to 0 to infinity n square into probability of n. And probability of n particle is z to the n into z of n divided by q. So that is equal to 1 over n is equal to 0 to infinity n square z to the n into z of n divided by q. So this I will have to write it as so I write it as sum over n is equal to 0 to infinity z dou by dou z into z dou by dou z dou by dou z of z to the n into zn over. Okay, so that I think is, so when you write dou by dou z, you get n into z to the n minus 1. When you multiply with this z, it becomes z to the n again. So you get the same thing. So this implies that I can write this as z dou by dou z the square acting on 1 by q. 1 by q is outside into this is will become q. So you can see that it would be 1 by q into z dou by dou z of z into q. Sorry, z into dou q by dou z. It's equal to 1 by q into z into dou q by dou z plus z times dou square q by dou z square. So that is 1 by q into z dou z plus z square dou square q by dou z. Okay, so this will be like and if you look at this term, the first term is z into dou by dou z of logarithm of q plus 1 by q into z square into dou square q by dou z square. But this we know is average value of n. So we can write down average n square minus average n. No, sorry. So cannot write from here. So here you can write it as average n square is equal to 1 by q into z to q by dou z plus z square, and you already know that z by q into dou q by dou z is equal to average value of n. Okay, so you can write this dou by dou z of dou q by dou z, and you can write down this dou q by dou z as average Q or Z into the Q by the Z. You can write it like this. That means maybe even in slightly at an earlier stage, you can substitute that. Let's say at this stage, the average N times Q. So that gives you that the average N squared is equal to Z divided by Z of N into numbers. So Z by Q into I have average N into the Q by the Z plus Q times dou N by dou Z. Okay. So this is equal to, this is N, and Z by Q into dou Q by dou Z is another N plus Z into dou N by dou Z. So this is also N. So this is N square. That means you have average N square minus average N the square. This is the variance in N, and that is given by Z into dou N by dou Z. So this derivation, whatever I have written here, is in general true for a single particle or many particles. So now suppose if you want to write a single particle, the average N is equal to 1 by Z to the e to the minus beta epsilon plus 1. So what will be dou N by dou Z? That is equal to minus 1 by Z inverse, or I could have written this as N is equal to, I can take this Z e to the minus beta epsilon divided by 1 minus Z into e to the beta into minus beta. And this is how I get this one. Right? So dou N by dou Z will be equal to e to the minus beta epsilon divided by 1 plus Z into e to the minus beta epsilon minus Z into e to the minus beta epsilon divided by 1 plus Z into e to the minus beta epsilon the whole square into e to the minus beta epsilon. So I can write this as e to the minus beta epsilon divided by 1 plus Z into e to the minus beta epsilon. I can write 1 minus 1 minus Z into e to the minus beta epsilon divided by 1 plus Z into e to the minus beta epsilon. Okay, so I have taken this out. Okay, there is also a Z sitting here, right? So this is just this one. So if I want to write Z into this, so this whole thing into Z, that means this is Z. But what is this quantity? This quantity is N bar, or whatever, N. So this n into 1 minus n. So this will be your variance. So I think whatever option A or B is. Yeah, first
Yes,
option.
sir. Option A, sir. That's the option. That's the correct answer is given, sir.
Yeah. This A.
A is sir, A is the correct option, sir.
Yeah.
So can you please explain, like, this is so complicated, how to arrive at?
Oh, what I'm saying is that as far as up to this point, where up to this point, like up to this equation, I have been very general. So this could be the total number of particles, or this could be average number of particles per single particle state. This is same for bosons and fermions. So this is a general expression for a canonical, grand canonical partition function. Because in deriving this, I have just assumed only grand canonical partition function. Correct? So this is average. This is the variance of any system. So grand canonical ensemble, variance of any grand canonical ensemble. Now, if you want to talk about average number of particles for single particle energy for fermions, then I have to use this expression for fermions. Okay. So this expression I am simply writing it as. So this expression is same as this expression. Right? Then I am writing z into dou n by dou z, and writing it in terms of again average n. Correct?
Okay, sir. Understood, sir. Should I say the next question, or like someone else should?
Yeah, whoever is ready.
Yes, really. So anyone else?
Okay. I before that, before I forget, I wanted to ask you whether there was any progress with some questions that we left yesterday. I think the first question you asked was about this
Dispersion relation.
So I think whatever we have discussed here, this seems to be the way that we have to do. So like you can say that n is equal to integral from 0 to, let's say, some kf. This is a Fermi wave vector, and g of k dk. Okay, and this is given to be 1 by 3. Okay, this is not density of states, not in terms of energy, but we can also we wrote this yesterday. So, but we have to calculate this g of k in one dimension. That also we wrote yesterday. In one dimension, you have dk is the length, and then a by 2 pi is the number of states per unit length, and then there is a factor of 2, which is because of the spin of the electron. So this will be your what is called the g of k dt. Okay, so if I substitute that here, it is equal to 2 will cancel, so I have a divided by pi and integral 0 to kf simply dk. So that gives you simply a by pi into kf. Okay, so that gives you your kf times a to the pi by. Okay, so now once you have this, you know this dispersion relation, epsilon of k. I think we have this terms of sine squares and cos squares.
Sir, I will tell you, sir. 2 epsilon naught
Yeah, so 2 epsilon naught
within brackets sine square k by 2
sine square ka by 2
minus 1
minus
6
1 by 6
sine square k.
by k. Correct. So now I want epsilon f. That means I have to substitute wherever k is there, k. So sine square kf into a by 2 minus 1 by 6 sine square kf into a. But we have already determined what is kfa, so that's equal to 2 epsilon naught into sine square pi by 6 minus 1 by 6 into sine square pi by 2. So sine square pi by 6 is 1 by 4 minus 1 by 6 into 3 by 4. So this is equal to 2 times epsilon naught into 1 by 4 minus 1 by 8. So this is equal to 2 epsilon naught into 1 by 8. That's equal to epsilon naught by 4. So I don't know if that was there in the choice.
Yes, sir, option A is epsilon A by 4, epsilon naught by 4.
Yeah.
Yes, sir, but absolute value of k is greater than equal to pi.
That part, that condition was what actually was troubling me yesterday. But I think that condition is either it was a mistake, or I believe that it may be Ka modulus is less than or equal to pi.
That only printing mistake might be.
Maybe because it should be dispersion relation within the first Brillouin tube. In which
Okay,
case, I think this is correct.
Okay, thank you, sir.
Yeah. Yeah. So go ahead next.
Sir, a charged spinless particle of mass m is subjected to an attractive potential V of
What
xyz.
potential?
Attractive potential V
Yeah.
of xyz is equals to half of k x of k half k x square plus y square plus z square. Simple harmonic oscillator. Isotropic. Where k is a positive constant. Now a perturbation in the form of a weak magnetic field, capital B equal to B0 k, B equal to B0 k, k cap, where B0 is a constant, is switched on. Into how many distinct levels will the second excited state of the unparted Hamiltonian split?
Second excited state.
Yes, sir. Into how many distinct levels will the second excited state of the unparted Hamiltonian split? There are 4 options. Option A is 5. Option B is 4. Option C 2. Option D 1.
So you know that n is equal to 0. This is the ground state, and that has a degeneracy. D0 is 1. N is equal to 1 is it has a degeneracy of 3, and so you have second excited state. That's correspond to n is equal to 2. Okay, so I think there is a general formula for this isotropic three-dimensional harmonic oscillator, which I think is n plus 2 into n plus 1 by, because if n is equal to 1, then 3 n plus 3. So it's n is equal to 1. This is 4, 3, 4, 5. So n is equal to 2 means I have n1, n2, n3. So n is basically this one. So that means I may have 2, 0, 0, 0, 2, 0, and 0, 0, 2, or 1, 1, 0, 1, 0, 1, 0, 1, 1. So that I have 6. Degeneracy is 6. So that means 4 and 2 plus 3 is 5. Okay, I think this formula is just like our this formula. You have, let's say, d dimension, okay, d dimension, and n is your energy level, nth excited state. Then the degeneracy is given by n plus d minus 1 t n minus 1. So that's equal to n plus d minus 1 factorial into d divided by d factorial into n minus 1. So if you take n is equal to 2 and d is equal to 3, this is 3 dimensions. So this is 3 plus 2 is 5, 5 minus 1 is 4, 4 factorial divided by factorial 3 into factorial 1. So that gives you so I think this is n factorial and d minus 1 factorial. So 2 factorial and 2 factorial. So that will be 3, 4 divided by 1 into 2. So that is 6. So this is p n plus p minus 1 by. So this is the formula. Okay, so this is as far as the degeneracy is concerned. So each nth excited state will have a degeneracy given by this this expression that we have used in Einstein's theory also. Okay, so now the point is, if you are applying a magnetic field in the z direction, so if you have a Hamiltonian, your Hamiltonian will have p square by 2m plus v of xyz. Okay, so when you apply magnetic field, what happens? Your Hamiltonian will become p minus whatever is the charge qa whole square by 2m plus. Okay, so the general thing is that when apply magnetic field, p will be replaced by p minus q times. Okay, so that is and if you have electromagnetic field, then E will be replaced by E minus q times phi. So this is vector potential and this is scalar potential. Now the moment you have B is equal to a constant magnetic field B naught of K, then you can say that your A will be half B cross R. Okay, so this is vector potential for a uniform magnetic field. So you can find out that magnetic field, and then a weak magnetic field, right? It said that it's a weak magnetic field.
So let me check. It's weak magnetic field, yes.
Yeah. So it is said it's a weak magnetic field. That means when you are trying to expand this, you get p square by 2m minus p dot a minus a dot p dot p by 2m, and plus you have this q square and a square by 2m. So you can actually neglect this. Okay, so neglect it because it is weak magnetic. Weak. So you have to consider this one as your what is called the perturbation Hamilton. Okay, so now it turns out that you can show that this you can write this one. This A can be written as V naught into V naught by 2 into y times I minus x times A. Okay, so this will be the vector potential. If you calculate the vector potential using this formula, and you can see that P dot A is h bar by I into del dot A. Okay, and A dot P is A dot h bar by I put it out dot del. But what is this one? We can understand only when you operate this on some function psi. Okay, so let's say on some function psi. This is nothing but h cross by I into A dot del psi. Whereas if you operate this on a function psi, then this is operating on a function psi. This is equal to h bar by I into del dot A psi. Okay, so this can be written as h bar by I into del dot A into psi plus A dot del psi. Okay. So when you write it like this, so these are both are minus signs. So P dot A plus A dot P operating on psi will be equal to, so P dot A operating on psi is h bar by I into del dot A into psi plus uh, A dot del psi plus A dot P into psi is h bar by A is common, so A dot del psi. Okay, so we can there is Yes, there is a minus sign there. Yeah, I think that's fine. So it is like if you choose this particular A, then del dot A term will be 0, and this becomes simply 2h bar by I into A dot del. So that is equal to 2h bar by I into B naught by 2 into Y times I minus X times J dot plus I by dou X plus I plus I by dou Y times J I by dou Z times A. So you can see that this 2 will cancel. You have B naught plus by I into y dou psi by dou x minus x dou psi by 2. So this is nothing but we have b naught into y x minus x e. These are the operators of this. So, but this is nothing but minus b naught times Lz operator. Correct? So this is so your perturbation Hamiltonian is related to Lz operator. Now you can see that in this harmonic oscillator, we have potential is half a r square. That means this is central potential. That means the angular momentum is conserved. So Hamiltonian, L square, and Lz. These three things will form a complete set of complete set of compatible accelerators. So we can work with this. Already it is given that it is spin zero particles, so these three will be complete set of particles. Now, but whatever the n that I have shown here is so your Hamiltonian. If you write it in terms of spherical polar coordinates, so your h can be written as some pr square by 2m, this is the radial momentum, plus L square by twice m r square, this is the centrifugal the angular momentum part of the Hamiltonian, plus v of r, that is half kr square, half kr square. So this is your Hamiltonian, and now you have a minus sign, minus and minus will become plus. Plus you have q times v naught by 2m into LBC. Okay, so this is your Hamiltonian. So you're going to treat this as your perturbation. Because that is what is containing this V naught. It is applied here. So you can see that you will have this n l m. Okay, so the first excited state is 1 0 0. This is the ground state, and first excited state is 2 1. That is n is equal to 1 is ground state, n is equal to 2 is first excited state, n is equal to 3 is second excited state. Okay, so corresponding to n is equal to 3, you will have 3. So your L can be 0, 1, 2. Okay, and M. So if L is equal to 0, M is 0, and this M is equal to minus 1, 0, plus 1, and this one is M is equal to minus 2. Okay, but the energy will also depend on L, because so energy will depend on both N and L. It will not depend on L only for Coulomb potential. Okay, so in that way, if you look at the ground state, so 1 0 0 is the ground state, and 2, if L is increasing, then so this is your first excited state, and then 2 1 is the second excited state, and 2 1 M is the second excited state. And this will have a degeneracy of 3 levels. That is 2 1 1 and 2 1 0 and 2 1 minus 1. Okay. Now you can see that independent, because this central potential, without this perturbation, there is no energy levels don't depend on n. But this perturbation is going to be Lz. So Lz operating on this NLM is going to be equal to H bar M into NLM. That means it will depend on M. That means each one of this will have a different energy. So you will have a degeneracy. Earlier the degeneracy was 3. Now degeneracy gets lifted. So the answer is 3.
What's the option? 3 is not in the option, sir.
3 is not
5,
in the option.
I will check again. Okay, sir. The options are 5, 4, 2, 1.
5, 4, 2. Um, 2, 0, 3. This said second excited state, right?
Yes, sir.
Two, 1. So I think what I'm saying is that the energy should depend on N and L. So 100 is the ground state, and 200 is, and also there is a result that ENL is greater than ANL prime if L is greater than L prime. Because angular momentum increases, so the energy also increases. So that means we will have this as your first excited state. Then Q1M will be a second excited state. This will be degenerate, and when you apply this magnetic field, this degeneracy will get fixed. So the question, just last part of the question, can you read once?
Last part of the question. Now a perturbation in the form of a weak magnetic field B is equals to B naught K, where B is naught is a constant is switched on, into how many distinct levels will the second excited state of the unperturbed Hamiltonian split?
How many distinct states will it? Anyway, I think to me it looks like 3 is the correct answer, because it cannot be even, because it is always 2L plus 1, that is the degeneracy, whatever is the value of L. And this 2L plus 1, it will be what is okay, let me see. If, yeah, I think it's, there is one level, and one level will go up, other level will come down. So this is like whatever is En E21 is E21 plus h bar n into some constant. This V2 plus minus h bar n into some same constant. There will be 3 distinct levels. One level will go to 3 distinct levels. Okay, so it cannot be 1 because only ground state alone will not split. Okay, so since they are talking specifically about second excited state, it cannot be 5 also, because that means this corresponds to L equal to 2, which cannot happen for N is equal to 2. Okay, for me it looks like 3 is the correct answer. But you understood the point, right? I am trying to look at. There is all this mathematics is correct. So you have LZ as the perturbation Hamiltonian. So it will only split. It will only lift the degeneracy with respect to the eigenvalues of LZ operator. So I think 3 is correct. There is no reason why it should be any other thing. It should not be even number for sure. That you understand, right? It's spinless. So it should not be even number. It should be odd number. There are only 2 odd numbers in the choices, 5 and 1. So they probably think that the answer is 5. But how is it 5? So if they are thinking that n is equal to 1 is the ground state, n is equal to 2 is the first excited state, and n is equal to 3 is the second excited state, that means they are assuming that energy does not depend on L. which is not correct for harmonic oscillator potential. Harmonic oscillator energy levels will any central potential other than Coulomb potential will depend on energies depend on L. And you know, Coulomb potential alone has an additional symmetry that is called the Laplace-Runge-Lenz vector, and that is what is the reason for energy becoming independent of L also. For any other central potential, energy will depend on L. So now I cannot treat this as my second excited state in this case, because in this itself, 200 will be next lower energy and 21m will be next higher energy. In this also, if you are considering only 3 2m, okay, corresponding to this, you will get 5 distinct states. Okay, so if you are taking this 100, 200, 21m, 300, 31m, 32m. So this is first, second, third, fourth, fifth excited state. Only fifth excited state will have degeneracy of 5 and 5 distinct levels will come.
Sir, actually, I was disconnected.
So I'm saying that from all my understanding, it should be 3. It cannot be even, that you understand, because it is a spinless particle. It has to be 2l plus 1. Whatever is the l, it should be an odd number, and it cannot be 1 because it is not ground state. So they assume that the answer should be 5, but I don't think second excited state will be 5, because energy depends on L for every other central potential other than the Coulomb potential. So
Okay, sir.
I think the answer should be 3.
Sir.
Yeah.
Sir, I have a question. Can I present it?
Yeah.
Okay.
Sir?
Yeah.
Sir, the next question.
Just 1 minute. Jahang Pratap is presenting some question. We'll finish that.
Okay, sir. Okay, sir. I was disconnected, sir. Okay.
I could not see it yet. I think it is coming. Yes.
Is it visible now?
Yeah. But the
55th question. Yeah, 55.
The relativistic Doppler effect, sir, this is, I think.
Because the number of particles is very close. I think this is a direct formula, no?
Yes, sir. This is like root over 1 minus beta square by 1 plus beta square.
Which option you are saying?
Option A, I think.
along the direction. Do they mean that it is L by beta? Because it has to be some length, right? Option A does not have a length. So it must be L by beta into Rahman. Okay, yeah, I think this is just that Doppler, relativistic Doppler effect. I don't remember the formula now, but we can check. But
Okay, sir.
So mainly like
option A
how
should have L. Otherwise, dimensionally it won't be well. Yeah. What Ashwin?
so how does that corrugated metal sheet like what is the significance of that?
I think corrugated metal sheet is supposed to see. It is just moving. It is just moving with the uniform velocity. Theta c in x direction. If something is moving with the uniform velocity, then it will not emit radiation.
Mm,
Right? It should have some acceleration.
yes.
So I think this corrugated metal sheet is providing some kind of oscillations for this charged particle,
Okay.
and that is what results in the radiation. Radiation, if you want the radiation to be emitted, the charged particle should undergo acceleration. So the corrugations in the metal, I think, are responsible for giving that kind of acceleration to this, and thereby there is a possibility of electromagnetic radiation.
Okay, sir.
Sir, can you please explain that again, sir?
Now, what I'm saying is, if a charged particle is just moving with a uniform velocity, then it doesn't emit any radiation.
Yes, sir.
So if you want radiation, then it should undergo oscillations. I mean, acceleration should be there.
Absolutely. Sir, I think the in option A, 1 should be replaced by L by beta.
Yeah. That is required for the dimensions.
Yeah, okay, sir. Thank you.
Yeah. Yeah. So next.
Sir, should I present something like a question? Okay, sir. Sir, it's not getting presented, so I will tell you, sir. Okay, sir. Sir, consider three particles, A, B, and C, each with an attribute S that can take two values, plus minus 1. Let SA, sir, let S of A,
each can take two values.
it's a plus minus 1. Let S of A is 1, S of B is 1, and S of C is minus 1 at a given instant.
Okay.
In the next instant, each S value can change to minus S with probability 1/3. The probability that SA plus SB plus SC remains unchanged is, and there are 4 options.
Probability that SA plus SP plus SC
Remains unchanged
remains unchanged.
is
Okay. What are the options?
2/3,
Hmm.
1/3,
Hmm.
2/9, and 4/9.
Okay. So initially here, this is the initial state, right? Initial. 1 minus 1 is the initial state, right? Okay, so it can, so S of A, so SA goes to, it remains 1 with 2/3 probability, then goes to minus 1 with 1/3 probability. Same thing with SB and SC, it remains 1 minus 1 with 1/3 probability and 2/3 probability. So this should change. So this should so this 1 minus 1 can become 1 minus 1 1 or minus 1 1 1. Okay. So in this case also the sum is same. In this case also the sum is same. In this case also the sum is same. So in any other case, sum will not be same. So this is the initial microstate, and from this to this, what is the probability? So 1 remains 1. That means the probability is 2/3, and 1 goes to minus 1. The probability is 1/3, and minus 1 goes to 1. The probability is 1/3. And to do this, 1 going to minus 1, probability is 1/3. This remains the same, it is 2/3. This remains the same, this is 1. Sorry, this changes. 1 goes to minus 1, 1 remains same, and minus 1 goes to 1. So this is equal to 2/27, and this is also 2/27. So it could be this configuration, or it could be this configuration. In both the cases, it will remain the same. The sum will remain the same. Okay, so that means we have by 20.
Also, the options are 2 by 3, 1 by 3, 2 by 9, and 4 by 9.
4 by 9. So after that initial state, can you read the question once?
Okay, so consider three particles A, B, and C, each with an attribute S that can take two values plus minus 1. Let S of A is 1, SB is 1, and SC is minus 1 at a given instant. In the next instant, each S value can change to minus S with probability 1/3. The probability that SA plus SB plus SC remains unchanged is, and there are four options: 2/3, 1/3, 2 by 9, 4 by 9.
At another instant, S can change to minus S with the probability 1/3.
1/3. So there will be eight combinations, eight permutations, sir. So we have divided by total probability, no? Sir?
Yeah, but so this 1 by 3, the probability for each one of them is given, right? And they are independent.
Yes.
So are there more possibilities, or have I listed all of them for SA plus SB plus SB to be unchanged?
So totally there will be eight permutations.
Correct. So there are 8 permutations, but that is let's say 1 1 1 and 1 1 minus 1 and minus 1 1 minus 1 1 1 minus 1 minus 1 minus 1 minus 1 1 minus 1 and minus 1 minus 1 minus. These are the 8 possibilities. In this is what is given at an instant time, right? And the sum should be equal to constant. That means these are the only 3 possibilities. Correct? So this is already given at some time t. So in the next instant, it can go to this, or it can go to this, or it can remain there itself. That is also a possibility. So it can remain there means it is 2 by 3, 2 by 3, and 2 by 3. So that will be like 8 by 27. Okay, so then I will have 12 by 27. Yeah, that is fine. Then that is 4 by 9.
4 by 9.
You understand? You understand?
Yes, sir.
That is, it can remain here. Then that means each one remaining is 2 by 3, 2 by 3, 2 by 3. Or this can change. One can go to minus 1, this can go to 1. Like that. That is 2 by 27, 2 by 27. So these are 3 possibilities. So the sum of all the probabilities is 4 by 9.
Okay, sir. Okay, sir. Sir, next question. A pendulum consists of a ring of mass m and radius r suspended by a massless rigid rod of length small l attached to its rim. When the pendulum oscillates in the plane of the ring, the time period of oscillation is. There are 4 options:
You have this thing connected to a ring, is it?
A pendulum consists of a ring of mass M, capital M, sir,
Uh-huh.
and radius capital R,
Mm.
suspended by a massless rigid rod of length small l attached to its rim. When the pendulum oscillates in the plane of the ring, the time period of oscillation is.
Mm.
There are four options: 2 pi root over L plus R by G,
L plus
R by
R,
G, L
R by
plus
G.
L plus R
Ah.
by G.
Mm.
Option B is 2 pi by root over of G
2 pi.
by root over G
This one
times L square.
in the denominator itself.
No, sir. In the
Ah.
numerator, L square plus R square
Mm.
whole to the power 1 by 4.
Mm.
Option C is 2 pi root over
Mm.
2 R square
Mm.
plus 2 RL plus
Mm.
L square
Mm.
divided by G into R plus L. And option D is 2 pi by root over G
2 pi.
root over G
Mm.
times 2 R square
Mm.
plus 2 RL plus L square whole to the power 1 by 4. Yes, sir.
Mm. So it is oscillating in the plane of the ring only, right?
Yes, sir.
Plane of the ring. Okay, so there is you can actually think of this is a rigid rod, and you have theta as one coordinate, and there can be another coordinate which is so that is it is possible that you have a ring like this which will also have a oscillatory motion in this fashion. Okay, so that means this particular motion about the center of the ring. The ring can have or about this point, for example. About this point, ring can have a rotational motion. Okay, so which I will call it as some phi. So this will be 2 degree of freedom problem, theta and phi. Okay, so that is so if you have a ring, what is the so something like mr square. Mr square is your moment of inertia of the ring. So rotational kinetic energy of the ring is something like mr square into pi dot square. Okay. And kinetic energy of the translational kinetic energy is half m L square theta dot square. And your V is MDL into 1 minus cos theta. So when you are trying to look at L by is there a mass for the rod? Is that given?
Sir, it's a rigid rod of massless, sir.
Massless. Okay, if it is a massless rod, then you have to simply take the center of mass of the ring is at the center of the ring. Then it is like you have a point mass at L plus R distance. Okay, and it's just like a point mass pendulum. So your answer will be 2 pi square root of L plus R divided by this first question.
Okay, sir.
If rod has a mass, then you have to take the center of mass of the rod plus ring together.
Okay, so the radius of the ring plus the length of the rod, that is
Yeah,
L.
yeah.
Oh, okay, sir. So can you see the question? Hello?
Just a minute. Yeah, you have to expand it a little bit. I can't read it.
So can you pin it?
Consider an array of atoms. Is that the question? 68.
Yes, sir.
Consider an array of atoms in one dimension with an ensemble average periodic density distribution as shown here. K is the wave number. Elements of Fourier transform the density correlation mention the ratio of S K delta. Um, okay, I think it is easier to do this density correlation function. That means you have rho of x into rho of x plus y into dx or integral. This will be your, we call it cy, correlation function of density correlation. And your s of k is equal to 5 to 5 integral to the power I ky of t of y t. So if your delta is becoming 0, then you will have them to be a Dirac delta function. Correct? So if you are so if you have, that means you are having delta of x minus na sum over n is equal to 1 to infinity or something. So this will be your
So impulse train.
maybe there is a constant rho naught.
So Dirac comb, sir. This is
Dirac comb if your delta is equal to 0. So if you are trying to write c of y equal to integral, let's say rho naught square and sum over n and sum over m delta of x minus n into delta of x y minus n. And you do an integration over x. So if you do this integration over x equal to na, that's equal to rho naught square to sum over n comma n delta of minus na, so that is y minus n plus n y plus n minus n into a. And when I substitute this in this particular case, so my sk will be equal to more n comma n to the ik n plus into the ik into n plus n. On the other hand, if you have a real row of x into row of x plus y, dx. So let's say the C delta L equal to rho of x is 1 by delta, right? So if you are starting from a minus delta by 2 to a plus delta by 2, then this is 1 by delta, and this will be this will be again kind of a constant.
So actually, what is density correlation function, sir?
That's why I am defining it here. So you have the C of y is a density correlation function. That means you have density. Let's say that you have some kind of a density like this. Let's say this is your rho of x versus x. Then you have x, and you have a fixed distance y. So you start from here, and what is the correlation between the density at these 2 points? Now you go to this point and exactly ask what is the correlation after y. Okay, now you go on changing x, but fix your y. That will tell you what is the density correlation.
So does that come under statistical mechanics?
Yes, it is. Basically, this is somewhat. It's called linear response theory, which is kind of advanced statistical mechanics.
So you have told that the fluctuations is linear response. Like in the class, you have told that the fluctuations. So that is linear response theory, sir. Like if the system tries to reduce the fluctuation.
Correct. So basically, you have something like a stimulus. So stimulus is generally some kind of a force, and then there is a response. Okay, so response is F. Okay, so something like you have a parallel plate capacitor, then you apply potential difference, and then there is a charge accumulated on this. So this is like stimulus, and this is like response. Or let's say you apply electric field and there is a current. So you have this Ohm's law, right? So J is equal to sigma times E. So this is like stimulus, and this is like response. And if this J is linear to the stimulus, then you call that as a linear response. That is kind of an assumption, in the sense when you apply weak fields, you can assume that the response will be linear. Okay. So I think this question.
So I don't know this. I don't know this thing. So if it comes in the exam, I won't be able to answer. Like if I understand this also.
Yeah. But what I believe is that this particular topic is generally out of syllabus for CSIR also. Because it's not there in part C, part B, anywhere. But depending on the person who is setting the question paper, sometimes there will be questions from their research area and things like that. So I think we can safely leave such questions if you don't understand.
Okay, sir. Because okay. So the next question: a doubly charged ion in the angular momentum state, J equal to 2 and J equal to 1, meets a gas of polarized electrons.
Sorry, you read again.
A doubly charged ion in the angular momentum state J equal to 2 and J equal to 1.
Why 2 states?
I don't know, sir. It's given in the question. Doubly charged ion meets a gas of polarized electrons H3 equals to half and gets neutralized.
H?
S3 spin
S3
equals to half and gets neutralized. If the orbital angular momentum transferred in the process is 0, the probability that the neutral atom is in the J equal to 2, J3 equal to 2. Oh, sir, the next J equal to J3 equal to 1, I think.
J3 equal to
1. That was omitted in the question, so like printing mistake. So neutral atom is in the J equal to 2, J3 equal to 2 state is
J equal to 2 and J3 equal to 2.
Yes, sir. Options are 2 by 5, 2 by 3, 1 by 5, 1 by 3.
Okay, so this doubly charged ion is meeting an electron gas which has S3 equal to half, right?
Polarized electrons.
Polarized electrons with S3 equal to half.
Half, yes, sir.
Okay, so basically now what we have is that this is the problem in addition of angular momentum. So what we have is a state. Let's say this is J1, for example, first angular momentum. That state is given by 2, 1. And similarly, you have J2. J2 is your spin system. That is given by half, half. Okay. So, now now this is getting neutralized. That means your total angular momentum. See, this is 2 and this is half, and so the total angular momentum can be this is first thing is this is doubly charged, right?
Yes, sir.
Doubly charged. That means it is some kind of a, let's say, some O plus plus or something. O is not oxygen, any atom in the so O plus plus. That means it will take 2 electrons, and both the electrons are in half spin. So that means they can when these electrons go there. So this is half and this is half. So their spin can be 0 or 1. Okay, so when they go and attach to this one. Okay, this is the spin part of it. And so then in this case, you already have 2. That means the possible total angular momenta are, you can say that, so this is your J and this is your S. So it can be 0. So that means it is total angular momentum is 2. Okay, so I will call this as J here. And if this is 2 and this is 1, then this can be 1, 2, or 3. 1, 2, or 3. Okay, so if there is something called there is something zero, no? What is that? Total angular momentum or orbital angular momentum transferred is zero. Is that
Zero, yes, sir, zero.
orbital angular momentum transferred is zero? Okay, that means your this J has to be equal to the total angular momentum has to be equal to 3. That means this is one possibility and this is one possibility. Correct? So if
Sir, can you please explain that?
So that is in this particular case, this J1 is equal to 2. This is orbital angular momentum. Correct?
Yes, sir.
Orbital angular momentum. So the total angular momentum should have the same after the spins are getting added. The orbital angular momentum is 0. So if at all something is added, it is added only through the spin. Correct? So,
yes, sir.
So it is possible that you can have spin can add something like 0, and this is it can add something like 1. But anyway, they want you to know what is J equal to 2, right? Now J3 equal to 2. Okay, so that means from here I have to pick up this 2, and from here I have to pick up this 2.
Yes.
Okay. So now it is what is the probability that J equal to 2 and 2?
Actually, sir, I haven't started the addition of angular momentum yet, so that's the problem I'm finding difficult.
So then whatever I am saying also will be difficult to understand.
It's difficult for me to understand, sir. Okay, sir, should we go to the next question?
Yeah.
This is from the Ising model. The Hamiltonian of a one-dimensional Ising model of n spins n large is h is equals to minus j summation I equals to 1 to capital N sigma I plus 1, where the spin sigma I is equals to plus minus 1 and j is a positive constant. At inverse temperature beta equals to 1 by kBt, the correlation function between the nearest neighbor spins, like with an angular bracket sigma I plus 1 is. Option A is e to the power minus beta j divided by e to the power beta j plus e to the power minus beta j. Option B is e to the power minus 2 beta j minus. And option C is tan hyperbolic beta j.
Denominator. Oh, this is second option is only this much.
Yes, sir. Third option is tan hyperbolic beta j. Fourth option is cot hyperbolic beta j. So the doubt mainly is what is correlation function between the nearest neighbor spins. Like I know how to write the partition function in a Ising model from Ising model. Like
yeah. So essentially, this is the correlation function. This is an ensemble average. So canonical probability density is given by e to the minus beta h divided by the partition function. Correct? So the partition function is written as e to the minus beta j over I equal to 1 to n sigma I plus 1. Okay, and you have to do this summation over the set of this sigma I is equal to plus minus 1. Each one of them can be plus 1 minus 1 plus 1 minus 1 like that. Correct?
Yes, sir.
So if you write it like this, for example, let's say sigma 1 is equal to minus 1 to plus 1, sigma 2 is equal to minus 1 to plus 1. Like this, you write sigma n is equal to minus 1 to plus 1, minus 1 to plus 1. And then e to the power beta j into, we have sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 3, sigma 4. This is how your Cartesian function is, right? Sigma n minus 1, sigma n. Correct? So supposing if I do this summation, okay, sigma 1 summation if I do, so then I will have up to this it will be there, and this summation, let's say I implement, and what I will have is instead of sigma 1, there are two possibilities, no? E to the power sigma 2 plus minus okay, so what I'm trying to do is I'm trying to just say that let me write down this z as sum over sigma 1 is equal to minus 1 to plus 1 e to the power minus plus beta j sigma 1 sigma 2 into all other terms, because sigma 1 is there only in this one. Correct? So that means this summation will be e to the power beta j sigma 2 plus e to the power minus beta j sigma 2. This is what will be this. Correct?
Yes,
Because
sir.
sigma 1 I have introduced like this. Okay, so now of course I cannot take sigma 2 because sigma 2 also is minus 1 to plus 1. Okay, so if I now use that one, okay, so but then there is a sigma 2 sitting here. Okay, so that so suppose if I use that, then I will have first let's say sigma 2 is equal to plus minus 1. So first term will be e to the power beta j plus e to the power minus beta j, and second term is also e to the power minus beta j plus e to the power beta j. Okay, so like this you will have terms of this type. Okay, so if you see this, you can see this. You can see this for every pair you get two. There is some kind of a term which is equal to this is like cos hyperbolic beta j, and you are going to have so many. This is basically multiplication, right? So I have 2 times this, and there are 2 such terms. That means there is something 4 times this, and there are going to be n such terms. So roughly that will be my partition function. Okay, this factor may not be correct, but let us. So this will be cos hyperbolic. Now you are going to ask your sigma I sigma j I plus 1. So that is equal to, I will have same thing, that sum over all the sigma i's e to the minus beta plus beta j sum over I equal to 1 to n sigma I plus 1 into P of into the probability of the microstate. Okay, so that is essentially sigma I plus 1 divided by um, Z. So you can see that I want this factor to come out every time. So I can actually get it by taking a dou by dou beta of 1 by z into dou by dou beta of this z itself. So that gives me my sigma I plus 1 is equal to 1 by z into dou by dou beta of logarithm of z. So which is equal to 1 by j into logarithm of z is n logarithm of forget about the 4 cos hyperbolic of theta. So that is equal to 1 by j into n into 1 by cos hyperbolic theta j into sin hyperbolic theta j into j. So this j will cancel. So I'll have n times tan hyperbolic of theta. So I think the tan hyperbolic is the answer.
But sir, I have difficulty understanding this. Can you explain like what is the correlation function?
So up to what you have understood?
So the partition function.
You understood up to partition function?
Yes, sir.
Okay. So then what I'm saying is that ensemble average of any quantity, the ensemble average of any quantity is written like this, no? So for example, if I nothing, I have written is non that got erased.
Okay, sir. After partition function, I understood. If in the exam the partition function comes, then I will be able to answer.
No, it's not. It's very simple. See what I'm trying to say. Oh, I think my thing got 1 minute. It got closed. So what I'm trying to say is that probably you can't see, right? Are you able to see?
No, sir.
No?
Yes, sir.
You know what I'm saying is that if I have partition function, then I can write down the probability as this one. No, probability of any configuration like this. Correct. So now, if I want to write down this sigma I, this is an ensemble average of sigma I plus 1. That is nothing but sum over all these sigma i's, sigma I plus 1 into the probability. Okay, and now that probability is e to the minus beta h divided by z. Correct. So now to get this factor, what I am doing is I'm trying to divide this by del beta such that I get sigma I plus 1 here. Then I don't have to write like this. Is exactly like how we used to do average energy, right? So in that case, this ensemble average can be written as 1 by j into dou by dou beta of log z. I have already found out this z. So this correlation function, this is the name called correlation function, but this is essentially ensemble average of sigma I into sigma I plus 1.
Okay, sir.
I can get it like this.
Okay, sir. It's clear, sir. Sir, now one last question. So the range of the interatomic potential in gaseous hydrogen is approximately 5 angstrom. In thermal equilibrium, hello?
What is that? Range, is it?
Range of the interatomic potential in gaseous hydrogen is approximately 5 angstrom.
Okay.
In thermal equilibrium, the maximum temperature for which the atom-atom scattering is dominantly S wave is
Dominantly S wave.
S wave. It's a low energy scattering, I think. 500 K, 100 Kelvin, 1 Kelvin, 1 millikelvin.
Kelvin, 100 Kelvin,
1 Kelvin?
1 millikelvin.
Yes.
So, you have something like if you have temperature, then you can calculate this H divided by square root of 2 pi m K.
So thermal de Broglie wavelength.
Thermal de Broglie wavelength. And then you can take your K is equal to 2 pi lambda. Okay. So this is your A. Okay. So now this Ka has to be much smaller than 1 for S wave scattering. Ka actually should go to 0. Ka should go to 0. So for which temperature that happens, that we have to calculate. Okay. So maybe you can calculate that.
So is it a problem partial wave analysis?
Basically, there is no partial wave here. It's only that, okay, S wave you can call it as a partial wave, but they're not asking you to calculate any phase shift or anything here. Only just trying to ask you what temperature. This is essentially kind of thermal wavelength problem.
Yes.
Okay, I hope the session is useful and
Very useful, sir.
all the best.
Thank
Do
you.
well.
So anything you want to say, any tips?
I told you, yesterday, so don't get tensed
Okay,
and keep cool. You have prepared well. I think all of you should now take rest. Don't prepare too much. Don't revise till last minute. I don't know what you can enjoy in the lockdown, but enjoy for one day before the examination.
Okay, sir. Thank
Okay,
you.
all the best. Yeah. So tomorrow anyway we have our class, right?
Yes, sir. 10:30. Starts soon. Okay, sir. Thank you.
Okay. Okay, Ashley, any close?
Hello, sir. Thank
Yeah, yeah. Okay.
you. Good night, sir.
Good night.